So, sketching the graph to approximate a derivative. It is all about just thinking about or approximating what the slope sort of looks like, okay? And so if I am looking at a graph, okay, I'm just going to draw a graph of like a cubed function. Right? This is my function. In blue, I'm going to do that in blue. If I take a bunch of points on this graph and just approximate, and I mean this, just sort of about seas. This doesn't have to be, it's not an exact science. We're sketching a potential or an approximate graph of this. If I pick a point here and draw the tangent line, we did this with sine and cosine. What does that slope appear to be? It's definitely positive. It could be about 1 or 2 or something, right? About. And so this slope is going to be, I'm just going to pick a value. Maybe, and I'm going to do a rough seas, about seas. This slope here looks to me to be about 2-ish. Good? It's a little steeper than 1 maybe, but if you said it's 1, I would be fine with that. And your picture might look different than my picture. Okay, maybe you didn't draw it exactly like me. But if I find another point here, and I draw the tangent line again, I'm going to try and do my best tangent line here. Draw the tangent line again. What does the slope of that line appear to be? Still positive, right? But flatter than 2. So this could be maybe 1 or maybe a half. I'm going to call mine about 1, because that's what mine appears to be for me, because I know what 1 looks like. If I look at a slope of 1, it's sort of almost like a 45. If I could draw a bottom line, it's about a 45-degree angle. And then I'm going to find another point. This is the one I like the best, because this one there's no approximating. What's the slope on that guy?
Zero.
Flat line, yeah, 0. Great. And what I do as I go through and approximate my slopes, and in fact, the easy ones to find are the 0 ones, because those always happen when we're changing direction. I can find one in between here. My graph is getting a little bit messy. But when the graph here is decreasing, what kind of slope do I have? Negative slope. And so my slope there is roughly, again, I don't know, maybe negative 2-ish. And I pick another point over here, and my slope looks almost parallel to the first. So I'm going to give my slope of roughly 2 again. Again, just an approximation. That's all I'm doing, is I'm finding tangent lines, and I'm approximating what the slope is. And then what I'm going to do is, just like we did with sine and cosine, I'm going to put it on a graph. Okay? So if I could sketch this graph on a coordinate plane, I'm just going to randomly put a coordinate plane in there. And I'm going to put another coordinate plane next to it. And I'm going to start plotting these slopes. So the first value that I had, bless you, on the far left had a slope of about 2. So I'm going to approximate that slope about 2. And then as I moved a little bit closer to the y-axis, I had a slope of about 1. Oops. move that. Slope of about 1. And then as I moved a little bit closer to the y-axis, I had a slope of 0. And then as I moved a little bit closer, I had a slope that was negative. And then just on the other side, I had another slope of 0. And then as I moved along, I had another slope of 2. And then I'm going to sketch this and create my graph of my derivative. I made it look like a parabola. Why did I make mine look like a parabola? If this is a cubed function, if f of x is x cubed, what is f prime of x? It is. It's actually 3x squared. What are squared functions? Parabolas. That's what they look like. And so when I sketch, or when I have a cubic function, if I'm going to sketch its derivative is going to be a parabola. If I have a parabola, a squared function, its derivative is going to be linear. And when I'm sketching the derivatives, I want to make them look like the nature of the function that it is. So cubed functions have derivatives that look like parabolas. Parabolas have functions that have derivatives that look like lines. Fourth powers have derivatives that look like cubic functions. And so whenever I graph my derivatives, my f prime, an approximate, I want to think about what is the nature of the graph that I started with? What does it kind of look like? And if I derive that, take the derivative, what is that graph going to look like? Okay? And then I start plotting approximate slopes on there. So let's look at problem number 1, and I'm going to graph this I'm going to graph the derivative right on the graph. Okay? The first thing that I always want to find is where my graph is changing direction. And I also want to think about what I'm looking at. So this is an upside down parabola, yes? Okay? And so if the original function is an upside down parabola, its derivative will be what? A negative line. So what do negative lines look like? They drop from the left to the right. And so I know that I'm going to have a line that sort of looks like that. Or I'm going to make a line, its derivative is going to look like that. Where does this change direction? Right at x equals 1. That's where the slope is 0. That's where the first derivative is 0. So I know that my negative line is going to cross the axis at that point. Okay? Because that's where the derivative, right where it changes direction, it is where the derivative is 0, and my graph of my derivative is the graph of all the slopes, and this is the spot where the slope is 0. To the left of that line, what kind of slopes do I have? If this is increasing, my slopes are all going to be positive. And if I can approximate a slope, I would maybe call this, I don't know. Again, I could sort of count it up to, right, maybe it's 2-ish. I don't care. What I really know is it's positive. And so over here, I have positive slopes. Does it matter where I put it? No, it's positive slopes. What do I know about what my graph is going to look like? It's going to be a line. It's going to be a line that has a negative slope. So I'm going to go to the other region. What kind of slopes are to the left of the 0? Or to the right, sorry, of the 0? Those are negative slopes. So to the right of this point, I'm going to have a point in the negative region. I'm going to draw a negative line. I don't even really need to approximate these. I just need to know what this looks like. When I graph this, it is going to look like a negative line. What kind of function do I have for number 2? Looks sort of cubic. So it appears to be a cube function, kind of like the first one we did, the one we drew up on the top. What's the derivative of a cube function? A squared function. What does a squared function look like? It looks like a parabola. What is my derivative graph going to look like? It's going to look like a parabola. I need to figure out where it's changing direction. Here, that's where it crosses the x-axis. And here is where it crosses the x-axis. To the far left, this graph is increasing. That means they are positive slopes. Up until now, I approximated a slope, but I don't need to. I just need to know it's positive. If it's positive, it's in the upper region of the graph. I'm just going to randomly put a positive point up there, because my slopes are positive. In between the 2 points, in between the 2 spots where it changes directions, what kind of slopes do I have there? Negative. They're dropping. This graph is falling. That means in between there's going to be a point that's in the negative region. And I should be doing this in a different color so it stands out. So I have here, and I'm just going to put a point in a negative region. Does it matter where I put it? No. It's just in the negative region. And then I go to the other side of the 0. Here's my other side. What kind of slopes do I have there? It's increasing, so I have another positive point up here. What is this graph going to look like? A parabola. Connect the points and make it look like a parabola. You're not going to get a graph that is more difficult than a third power for this. Because what I want you to get out of this is the importance of where it's changing directions. Where it is changing directions is always where the slope is 0. And so that's going to help me find a point on my graph. So again, I look. What kind of graph do I have? Looks like one, two, three changes in directions makes it cubic. Because it is rising on the left and falling on the right, it's actually a negative cubed function. What's the derivative of a negative cubed function? Negative squared function. All these things are things that you learned in Algebra 2. Maybe you don't remember them completely, but think about what that sign does. Remember, a regular cubed function goes to negative infinity on the left to positive infinity on the right, because when you cube negative numbers, they're going to stay negative. When you cube positive numbers, they're going to get positive. If I flip it around and opposite, it's going to flip directions. Just like a parabola, positive opens up, negative opens down. What kind of parabola do I have here? One that opens down. So if I know that, that's going to help me a lot. My derivative graph should look like an upside down parabola. Right here, that first point where it changes directions is where the slope is 0. So I put that on the x-axis. The next spot that it changes direction is where the slope is 0. I put that on the x-axis. And then I sketch my graph. It's an upside down parabola. The slopes here are negative, then it goes to positive slopes, then it goes back to negative slopes. That means it's below the x-axis, above the x-axis, below the x-axis. Because this is a negative region, this is the positive region of the graph, and this is the negative region of the graph. So all I'm doing really is approximating the slopes. Again, know what your function is and know what its derivative is, and that'll make drawing your graph of the derivative a little bit easier to go through. Okay? What kind of graph do I have next? Definitely squared. What's the derivative of a squared? Yeah, linear. First power. Is this a negative squared? No. It opens up. If it were upside down, it would be a negative squared. This one isn't. So I know I'm going to be graphing a line. Where does my line cross the x-axis? Right where the slope is 0, and that looks like to be about 2. What do positive lines look like? Yeah, they rise from the left to the right. Does it matter how steep you make your line? No, I don't care. Just show me that you know. The derivative of a squared function is a linear function. I just need to make my line cross in the right spot. I'm going to have you guys try one. Let me do, I'll just draw it right. I'm going to draw it on the bottom here. Here is the graph that I want you guys to see if you can draw the derivative to. Just a nice quick one. See if you get the gist of it. There's my graph. I'm saying no more. See if you can graph the derivative of this graph. So 0 slopes again. That spot where it changes direction is where the slope is 0. That spot where it changes direction is where there is a turning point in my graph. Those turning points are known as relative extrema. That's basically high points, low points, or relative minima and maxima. We call them extreme values. And I use the term relative because it isn't necessarily an absolute max of the function or an absolute low point of the function. It is just a point where it hits at a peak and then turns around, or bottoms out and turns around. So for example, I can have a graph that changes direction several times. And this spot here is known as a max. And this spot up here is known as a min. However, my min value is higher than my max value because of the way the graph looks. That's why we call them relative. It's relative to this region in the graph. This is a low point here. This is a high point here. And we find those relative mins and maxes, or better than that, we find where this is changing direction. when I find my slope equal to 0. So what does that mean? I just need to figure out when the derivative equals 0. So before I get into problem number 5, tell me about the function in problem number 5. What do I have there? Squared, which looks like parabola. In particular, what kind? Negative, so it's going to open down. So what do I expect to see on this graph? This point is what? A max. It's a high point. And so this parabola is going to have one max value because there's one place that it changes direction. I want to find where that is. So I take my derivative, dy dx, and set it equal to 0. Then I'm going to solve for x. And I have a turning point here at 1. Now I know it's a max, but we do something called a prime chart. I'm going to call it a y prime chart. And this chart is going to be necessary when I do cube or fourth power functions or a rational function like this one, where I don't even really know what that looks like right now. I knew this was a max, but I don't always know it's a max. And so this y prime chart is what helps me figure out if it is a max or a min. What I do with here is I do little test points. I know at 1 the slope is 0, right? I know that that's where it's changing direction. I figured it out here. How about a point to the left of 1? Let's say I try something like 0. I'm just going to do a test point at x equals 0. And I hardly ever even write that down. I just wanted to write it down for your notes. This is a y prime chart, so I'm going to test this value in my derivative. So I want to figure out what negative 2 times 0 plus 2 is. What is negative 2 times 0 plus 2? 2. That's a positive area. And what that means to me again is, if this came out positive when I plugged in 0, and 0 is in the region to the left of 1, then any slope I would have put in here, or any value I would put in this derivative, is going to also come out positive. If I put in negative 1, if I put in negative 2, if I put in negative 3, if I put in negative 100, I can put in anything to the left of positive 1. I could even put in 0.9999999, and it's still going to come out positive. So this is a positive region. That means that on this side of my graph, up to 1, this is increasing. And so I draw a little curve, because that's what these polynomial graphs are. This is a little curve. It's increasing up to 1. Then I'm going to do a test point to the left of 1. I'm going to try test point x equals, give me a number to the left of 1, or to the right of 1. 2. Great. So I'm going to do negative 2 times 2 plus 2. What is negative 2 times 2 plus 2? Negative 2. That is a negative value. That means this is a negative region of the graph. Again, you could try any number that is to the right of 1. 1.1, 3, 10, 100, a million, anything you want to the right of 1. If you plug it into that derivative, it should come out as a negative value. That means that this is the region of the graph where it's decreasing. That shows me, just by those slopes, from increasing to 0 to decreasing, I can very vividly see that that is a high point or a max. So we say there is a max at 1 comma something. I want to find the point that is paired with 1. If I plug it into the derivative, it's going to give me the slope at 1. I don't want the slope at 1. I want the point at 1. So to find this value, I need to plug 1 back into the original equation. Turns out it's 0 anyways, and so this parabola changes direction at the point 1, 0. Now the parabola we knew what it looked like. We went into that knowing it's a max. I don't know what this one looks like. I'm not sure. I don't know if this is curvy. If I have a graphing calculator, I could plug it in and see. But what I want to do is figure out where it's changing directions. And I find where it's changing directions when the first derivative is 0. So I'll start with the first derivative. Low d high minus high d low over low low. Set it equal to 0. I'm going to do some cleanup while I'm at it. This is 6x squared plus 12x minus 3x squared. I can actually combine that together too. So 0 is 3x squared plus 12x over 3x plus 6 squared. Okay, I need to set that equal to 0. And I want to solve for x. I want to find the x value where this is changing direction. How do I start to solve something that has a variable in the denominator? How do I get the denominator out? Multiply, yeah. Yep, just multiply. So I'm going to take this and multiply that denominator right out of the bottom. I don't even care that it's squared. Just going to get rid of that whole bad boy. So it cancels it out completely. What happens when I multiply it by 0? It becomes 0. Yeah. So I have 0 equals 3x squared plus 12x. All right. I've run into another little problem. How do I solve a squared function? Can't do the square root because I have a non-squared term in here. Factor to solve. Can I factor out a GCF? Yeah. This is 3x times x plus 4. And then what do I do with those factors? Beautiful job. When does 3x equal 0? When x is? 0. When does x plus 4 equal 0? When x is? Negative 4. Great. So I have, what I just found is 2 spots where this graph is changing direction. Okay? 2 spots. I don't know what's what though. Is one a max and one a min? Are they both maxes? Are they both mins? What's going on here? So this is where I do my y prime chart. My y prime is a dy dx chart. It's a derivative chart, and I'm going to put these values on here. I treat this as a number line. And I do test points in the derivative. I do not need to worry about the denominator here, because no matter what I put in, I'm going to square it, and it's going to become positive, and it's not going to have an effect on anything. So all I'm going to do is do my test points in this guy. That's what I'm going to use for my test points. All right? And I'm going to do them just really, really basic. Really basic test points. Again, I went into a lot of depth on this one. I don't do that. I'm going to pick a number to the left of -4. Give me a number to the left of -4. -5. Great. You can use any number you want. Anything to the left. -10, -100, whatever you want. So -5. If I multiply 3 times -5, what kind of number do I get? Negative. If I do -5 plus 4, what kind of number do I get? Negative. What happens when I multiply a negative times a negative? So this is a negative times a negative region. This is a positive region, and it doesn't matter what number I put in there. All the slopes are going to end up being positive. And then I want to do a test point between -4 and 0. -2. Great. Again, it can be any number between -2 and 0. I'm going to go through that same process. What happens when I do 3 times -2? What kind of number do I get? What kind of number do I get when I do -2 plus 4? What do I get when I multiply a negative number times a positive number? That means this is a negative region. So what this tells me is, up until -4, this graph is rising. Here's me rising, right? At -4, it starts dropping. At 0, it changes direction again. Maybe it's going to drop some more. I don't know. I'm going to do a test point and see. Let's put in something to the right of 0. 2. Super. What kind of number do I get when I do 3 times 2? Positive. What kind of number do I get when I do 2 plus 4? What product or kind of product do I get when I multiply 2 positives? Okay, so yes, this is in fact turning around and increasing. When I visually look at increasing to decreasing, I find a max. If I'm rising and then dropping, that's a high point. If I'm dropping and then rising, that's a low point. So I say that I have a max at -4 comma something and a min at 0 comma something. How do I find those somethings? Original equation, back up to the top. So to get this one, draw an arrow down to get that one, I'm going to do -4 squared over 3 times -4 plus 6. -4 squared. That's my original function. Y equals, that leaves me with 16 over -6, I believe, or -8/3. So that is the exact point in which there's a max on this graph, and then I'm going to find the 0 pair. So that's y equals 0 squared over 3 times 0 plus 6, which is 0 over 6, or 0. So I have a min at 0, 0. find your derivative, set it equal to 0, do test points around those locations to figure out if you have mins or maxes. It is helpful if you know the equation or what kind of function you're graphing or looking at in the first place. For example, for problem number 7, I have a cubed function. I kind of know what this looks like. Cubed function, I'm probably going to have a max and a min. I need to find where, and so I'll do my derivative. I will set that equal to 0 and factor. I can't take anything out of 3, 28, and 60, so I'm just going to have to snowflake this or guess and check or however it is that you need to factor. That's your own personal. The top is 180. The bottom is 28 if I use snowflake. 3x and 3x. I need two numbers that multiply to be 180 and add to be 28. (18 and 10). Confidence, confidence. 18 and 10. It is. Yep. And then I can reduce this guy. So that is x and 6. And over here I can't. So my factors are x plus 6 and 3x plus 10. Great. So I had a square just like we had in that last problem. I had to factor it to solve, but I couldn't factor out a GCF, so I had to do factoring a trinomial. X plus 6, 3x plus 10. I'm going to set those equal to 0. X plus 6 equals 0 when x is what? Negative 6. And 3x plus 10 equals 0 when x is? Beautiful. Thank you. Great. I found 2 points where it changed directions. That's exactly what I thought, because this is a cubed function. Now I need to figure out which one's a max, which one's a min, and what the points are that happens. So which of those two numbers is furthest to the left, negative 6 or negative 10 thirds? Negative 6. So I'm going to go over here, negative 6. Negative 10 thirds, I'll put there. Remember, negative 10 thirds is negative 3.3 repeating, just to get an idea of about where that is when I'm trying to find my test points. And I want to test something to the left of negative 6. Give me a value.
Negative 7.
Negative 7, great. I'm going to be looking up here. This is what I'm going to look at. That's my derivative. That's what I'm going to use. This is a y prime chart or a derivative chart or an f prime chart or whatever you want to call it. It's a derivative chart. And so I'm checking the derivative, which means I'm checking the nature of the slopes. At negative 6, the slope is 0. That's what I found. Before negative 6, to the left of negative 6, is either rising or dropping in order to change direction. So negative 7. What kind of number do I get here? Here. So I have a negative times a negative. Definitely a positive region. That means I'm increasing up to there. Give me something between negative 6 and negative 3.3.
Negative 4.
Negative 4, negative 5, doesn't matter, right? What if I put either negative 4 or negative 5 in here? Positive. Here, negative, which makes a negative region, which means I'm dropping up to 10 thirds. Remember, and I draw those little things on there like I'm drawing curves. I make them like waves, because that's what we've got going on here. These are like waves. And so it's going to increase and then turn to 0. It'll slowly stop increasing, turn to 0. It'll decrease. It'll slowly stop decreasing and turn to 0. And now I need to check the region to the right of negative 3.3. Give me any number. Negative 3.2. All right. What do I get when I do negative 3.2 plus 6? Positive. What do I do when I do negative 3.2 times 3 plus 10? That's going to be 9.6 plus 10. Or sorry, negative 9.6 plus 10. Positive again. Positive region. Now, a question that I get often is, does it always go positive, negative, positive, or negative, positive, negative? No. There are instances where we go positive and then we stay positive. And that's a twist in the graph. We're going to see those at some point, okay? So don't all automatically make the assumption that, oh, I got positive, so the next must be negative and the next must be positive. Doesn't work that way, okay? Do your test points and check it out. All right, so I found a max where? At negative 6, and I got to find what it's paired with. And I found a min, or a mun, if you spell it like I do, at negative 10/3, and I need to find what that's paired with. Again, to find that value, I go back up to the original function, so I want to do negative 6 cubed plus 14 times negative 6 squared plus 60 times negative 6 plus 76. And you got 4? Excellent. Anybody agree with that? Yep, I got a couple of nods. Awesome. I'm going to do this next one. Negative 10/3 cubed plus 14 times negative 10/3 squared plus 60 times negative 10/3 plus 76.
Negative 5.481.
Okay, anybody agree? Negative 5.481, like what repeats?
The 481.
The whole 481, 481, 481. Great. Okay. Does that seem reasonable? Good. You might have gotten something, I think it's over 27 if you put it as a fraction. What'd you get?
Negative 148.
That's negative 148 over 27. Both of those answers are fine. Probably when we get to sketching it, this value is going to be more helpful because I know about where that is. Okay? And we're just going to be sketching them on a graph. All right, one last one. I know, I talked so much. I'm sorry. But one more. I've got a fourth power. Remember what a fourth power looks like? It's like a W or an M. So I might have 2 maxes and a min, or 2 mins and a max. Or it might have a twist in the graph and then I won't see a min or a max. But let's get into taking our derivative. I'm going to find my mins and my maxes when the slope of the tangent is 0. So dy dx is negative 4x cubed plus 8x, and the 0 is out. Oops, and I wrote said cubed, I wrote squared. Sorry about that. You can tell it's getting close to the end of the year. All right, so, how do I do a cubed? I can start with a GCF. I can definitely take out a negative 4x from both of those. Yeah? And then that leaves me with x squared minus 2, if I did it correctly. And now I need to set negative 4x equal to 0. And x squared minus 2 equal to 0. Because that's a difference of squares, but it's not a pretty difference of squares. And in fact, if I were to factor this, because it's a squared, it would be the square root of x squared, which is x, and the square root of 2, which is the square root of 2. and one would be plus and one would be minus. That's a difference of squares, okay? Not a pretty one. Oops, you can't see it though. So here I am, right there. That's what I meant. Or I can add 2 and take the square root of both sides. I just have to remember to do the plus or minus part. So I have 2 spots there, which makes sense to me because I'll have 1 spot here and 2 spots there. That'll give me my 2 maxes and my min, or the other way, my 2 mins and my max. Divide by -4, and that one's at 0. So now I'm going to make my little prime chart to help me out. This little prime chart is just going to be used to help me figure out what's happening to the slopes on each side of these critical values where it is changing direction. And so I have negative square root of 2 over here, 0 in the middle, positive square root of 2 over there. And my test points are going to happen in my y prime. Negative square root of 2 is like roughly negative 1.4 something. So I want something that is to the left of negative 1.4, negative 2. So I plug in negative 2 into this first piece. Negative 4 times negative 2 gives me a positive result. Negative 2 squared is 4 minus 2, also gives me a positive result. That means that in this region of the graph, I am increasing again. Increasing, and then changing directions at negative square root of 2. Give me something between negative square root of 2 and 0. Negative 1. Plug in negative 1 up here. Positive. Down here, or over here, negative, because it would be negative 1 squared, which is 1. 1 minus 2 is negative. So that's a positive, negative region, or a negative region of the graph, so it's going to drop and start to change direction at 0. So I'm dropping until I hit 0, because that's where it changes direction. And now I need to check to the right of 0. 1. Negative, positive region. I'm increasing up to the square root of 2. And then I'll pick something to the right of the square root of 2. 3, great. Again, it can be any number. It could be 100 if you felt like doing that math. So I put 3 in here. I get a negative value, negative 4 times positive 3. And then I put 3 in x squared minus 2. That's 9 minus 2. That's a positive value. Again, a negative region. And dropping there. That sure looks like what I expect a fourth power to look like, yes? An M or a W. I have 2 maxes. I have a max at negative square root of 2. And another one at positive square root of 2. And I have a min at 0. So I'll go ahead and plug those values in and see what I get. Again, this one is the opposite of negative square root of 2 raised to the 4th power plus 4 times negative square root of 2 squared minus 3. Nope, it comes out nice. You got what? 1? So it should be, this will be 4, so negative 4. This will be 2 plus 8. Negative 4 plus 8 is 4. 4 minus 3 is 1. Yep, that works. So that is 1. What do you get when you do the next one? The opposite of the square root of 2 to the 4th plus 4 times the square root of 2 minus 3. Actually comes out to be 1 again. That's my squared. Okay? What do I get when I plug in 0? And so there's my final answer. I've got a max at negative square root of 2, 1, positive square root of 2, 1, and 0, negative 3 is my mean. Whew, 50 minutes. That's a record.